A 1/12 scale model of an airplane is to be tested at 20 degrees in a pressurized wind tunnel. The prototype is to fly at 240 meters per second at 10 kilometers standard altitude. What should be the tunnel pressure in atmosphere to scale both the Mach number and the Reynolds number accurately? Okay, so first, let us put what do we know about the model and about the prototype. So for the model, the scale is 1/12. Okay, so this information can tell us that if we divide L model, so any characteristic lengths of a model, okay, over lengths of prototype is equal to 1/12. Okay, now for the model, the temperature of testing is 20 degrees. In general, they can give us the temperature because you know the fluid properties will be affected with the temperature. And I can give you, for example, tables. In these tables, you have for different temperatures how the density, the viscosity will vary, etc. Okay. And the prototype, for the prototype, we know that the velocity of the prototype is equal to 240 meters per second. At a 10 kilometer standard altitude. Also here, this can be given to determine the fluid properties because the altitude can affect the fluid properties. So all of this information, if you want, will be provided for you from tables. I give you tables that will allow you to find the properties for the conditions stated. So what should be the tunnel pressure? So we need to determine the pressure P in the model case. Okay. In order to scale both Mach number and Reynolds number in an accurate way. Okay. So first, from tables, we can go. So they gave us the altitude. From tables, we can search for air at 10 kilometer altitude. What is rho? So this information will allow you to determine rho of prototype. So rho prototype for 10 kilometer standard altitude is 0.4125 kilogram per meter cube. Okay, while for the model, we have sea level conditions. And for the prototype also, you don't only need rho, you know, whenever you have a fluid, you can search for all values required, the density, the viscosity, the sound speed. So all of these, okay, we'll get them from a table, okay, and we can put them. So we know also mu prototype. So this is mu prototype. And this is the sound speed. Why we need the sound speed here? Because they asked about the Mach number. And we know that the Mach number is by definition the velocity of the fluid, okay, over the sound speed in the same medium. So over A. And this value of A also is given from the tables at the conditions given. So since they gave you for the prototype the altitude, you can go to the to an appendix that will give you for this altitude what will be the properties rho, mu, and A. Okay. While at sea level, for the model, you are doing experiments at sea level, and we have the temperature. The temperature is provided, so we can read for this temperature what are the values of density, viscosity, etc. If we don't have the temperature exactly, if we don't find 20 degrees exactly, we can use like linear interpolation from tables, يعني like you do in thermodynamic tables. Okay. Now, second step is just to answer the question. Okay, we want to find. We know that whenever we want to extrapolate results from model to prototype, we need to satisfy the conditions that the dimensionless numbers are equal. So here we have to satisfy that Mach number in case of prototype is equal to the Mach number in case of model. Okay, and we know by definition that the Mach number is velocity over velocity of fluid over speed of speed of the sound. Okay, in the given condition. So we can write that Vp is given. Okay, so we have Vp over the acceleration, the velocity of sound in the medium for the conditions of 10-kilometer altitude. Also, we got it from the table, so it's 299. So also sound speed in prototype case is known, okay, equal to velocity of the model over sound speed in conditions of at sea level for a temperature of 20 degrees. So also we get this from the table. We have it. So the only unknown in this equality, okay, is the velocity that of fluid in the case of the model. Okay, so this will allow you to determine what is the velocity of the fluid in your wind tunnel. So now you calculate this parameter. Now, second condition, okay, the Reynolds number should be the same for both cases. Okay, so here when you solve, you get that the velocity in the model should be 273 meters per second. Now we move to the second condition, that Reynolds prototype should be equal to Reynolds in model. Okay, and we know by definition that the Reynolds number is density times velocity times characteristic length over mu. Okay, and as you know, we have the value of rho p, we have the value of Vp, we have the value of mu p. We don't have Lp, but we have a relation between L model and Lp. Okay, so the ratio will simplify, because now if you look at this expression, I will zoom a little bit. So if you look at this expression, okay, you have rho of the model is unknown. Rho of the model is unknown because we need to get the pressure in the model, and the pressure is related to density. Okay, since you know that for an ideal gas, you can relate the pressure to density by P equal rho RT. Okay, so in case you get rho model from this equation, you can deduce the pressure in the model by doing rho model times R, the gas constant, times Tm, which is the temperature in the model. Okay, so here we don't know rho m. It's true that we don't know Lp and Lm, but we know their ratios. Okay, so you can replace here Lm by Lp over 12, and then Lp will cancel out from your equation, and the only unknown will be rho of your model. So you will be able in this way to solve for the density of the fluid that should be used in your experiment, in your wind tunnel experiments. And since it's air and air is an ideal gas, can be treated as ideal gas in these conditions, then we can use that the pressure in the model in the wind tunnel can be calculated from rho RT. Okay. So in this way, we were able to determine what are the experimental conditions required, okay, to be able to extrapolate results from the experiments on the model of airplane to the real case. Any question on this problem? Okay. So let us move to problem 8. When tested in water at 20 degrees, flowing at 2 meters per second, an 8 centimeter diameter sphere has measured drag of 5 Newton. What will be the velocity and drag force on a 1.5 meter diameter weather balloon moored in sea level standard air under dynamically similar conditions? Okay, so again, here, if you want, in this problem, they are giving you a sorry, I had a connection issue. Do you see the screen again? Dear students, do you see the screen again? Okay, so I will move to problem 8. So when tested in water at 20 degrees flowing at 2 meters per second, an 8 centimeter diameter sphere has a measured drag of 5 Newton. So here we can start to put a table with the known values. We have, as usual, we have the model and the prototype. So for our model, first the fluid used is water. So we have water, and they gave us the temperature again. They gave the temperature to find all properties from table. Okay. So water at 20 degrees. This will allow you to go to your table and get. So you can get rho model
متعلقة
and viscosity of the
دكتور
model.
متعلقة
Simon? Okay. So you can go to the table and read the density and the viscosity. Okay. While for the prototype also, they gave us the condition of standard air at sea level. So these are rho prototype and mu prototype. So we know the characteristics of our fluids in both model and prototype. We need to find, if you want, conditions for the velocity that should be used in our model. Okay, so the question is here, no, it's in the opposite ways. We want to extrapolate results to get velocity and drag force in the case of the prototype. Okay, so we know everything here about the model. We have, this is the velocity of the experiment, of the fluid in the experiment, V model. This is the characteristic length in the model. So here we decided already on the conditions of the experiment. Okay. And under these conditions, we measured a drag force FD in model equal to 5 Newton. Okay. And according to these givens, we want to deduce what will be, so the unknowns are the velocity and drag force in the prototype. Okay. So V prototype and FD prototype should be measured. Okay. So here the two dimensionless numbers involved are Reynolds and drag coefficient. Okay, so all we have to do to ensure dynamic similarity between experiment and real case, so between the model and the prototype, we need to apply the equality conditions for groups. So the first group is the Reynolds number. The Reynolds number in the Dear students, sorry, the connection is really bad. Yalla, I will continue. I will share again. So first, to determine the velocity in the prototype, in the real case, we need to apply that
دكتور
Reynolds.
كتير عم بقطش الصوت.
Type guys, يعني the connection is bad. I'm really sorry for that. Yalla, just let us finish this problem. Okay, I will post the recording on the YouTube playlist. You can watch it again. Okay. So Reynolds model equal to Reynolds prototype. When we write this equality, the only unknown is the velocity of the prototype, so the actual velocity of
Okay,
the
dear, thank
balloon.
you.
We can solve for it, okay? And second, we need to determine the actual drag force acting on the balloon. So all we have to do is to say that the drag coefficient should be the same for both model and prototype. For the model, we have all information. They gave us the drag force, they gave us the characteristic length, velocity, and we got the density from the table. So we can determine drag coefficient for the model. And then in the drag coefficient of the prototype, the only unknown is the actual drag force acting on the balloon. So we can solve for it. Okay, we can solve for the force that is acting on the weather balloon at sea level. So it's very simple. In these two problems, we are showing you how we can extrapolate experimental results to real case results. The only condition is to satisfy similarity. Okay, so we should have kinetic, kinematic, and geometrical similarity to be able to extrapolate our results. Okay, any question on this? Okay, thank you. Bye bye.
Thank you.